In section 5.1, we're going to learn about inverse functions. Now before we do that, let's just recall what a function is. A function is something that sends inputs to outputs. So a function can be thought of as taking a certain input and then applying the function to it, and that sends it to a certain output. For example, 0 degrees Celsius in this example gets sent to 32 degrees Fahrenheit. And g is the function that does that sending. And similarly, 20 degrees Celsius gets sent by g to the number 68 degrees Fahrenheit, and 40 degrees Celsius gets sent to 104 degrees Fahrenheit. So the numbers on the left here are the inputs. Those are what we usually think of as the x's, or the independent variable. And the numbers on the right are the y's, or the outputs. Now, an inverse function does the reverse of this. It sends the outputs of the original function back to its inputs. So here's a picture of the inverse of the function g. Notice this green box represents the inverse of the function g. And it's going to take these numbers on the right and send them back to the numbers on the left. Now, that means the input of the inverse function of g were the outputs of the original function g. So what we should notice is the outputs of g become the inputs of the inverse of g. Similarly, these numbers over here on the left, these were the inputs for the original function g, but see, now they become the outputs of the inverse of g. So we can see that the inputs and outputs get interchanged. So the inputs of the original function are the outputs of the inverse, and vice versa. In this application, the original function g converts a Celsius temperature to a Fahrenheit temperature, but the inverse of the function g does the exact opposite. It converts a Fahrenheit temperature to a Celsius temperature. So this leads us to a very important fact. If we know in the ordered pair a comma b is on the function f, then the ordered pair b comma a will be on the inverse of f. And that's just because the input becomes the output and the output becomes the input. So the x and the y coordinates of an ordered pair get interchanged. Now we need to have a notation or a way of writing down the inverse of a function f. And the way we do that is the following. The notation is f with a -1 as a superscript. It kind of looks like an exponent, but it really isn't in this particular context. That's just a special notation to represent the inverse of the function f. So whenever we see this symbol, f with a -1 superscript, we know that represents an inverse of the function f. And similarly, if it was g instead of an f with a -1, then it would be the inverse of the function g. So we can say that if f of a equals b, then f inverse of b equals a. Now, really what that says is that if f sends a to b, so a is the number being sent and b is the number being sent to. So this notation, f of a equals b, means a is being sent to b by the function f. Then f inverse would send b back to a. Okay, so really this first statement here means the ordered pair a comma b is on f. And this second statement means the ordered pair b comma a is on f inverse. We call that. Okay. Okay, let's just try an example working with this notation. Here we have a table of inputs and outputs for the function f. and we want to find f of 2. Now that means if 2 is the input, what does f send that to? So we need to look for 2 as an input and see what the function f would do to that. So here's 2, here's the input, and see f sends that to the number 6. So the answer here would be 6. Okay, now let's try f of 6. So in this problem, 6 is the input, and we want to see what the function f sends that to. So here's the number 6 as an input, and that's getting sent to 486. Now this next one's a little trickier because we're trying to find f inverse of 2. So 2 is an input for the inverse function. Now that means it must be an output for the original function. So we have to find 2 as an output in the original function, and f inverse would send that 2 back to the number 1. Now let's try f inverse of 6. Now again, in this one, since the function is f inverse, if 6 is an input for f inverse, it must be an output for the original function f. So we have to find 6 as an output for the original function, and then f inverse would send that back to its original input, which would be 2. So basically, the original function, like in these first two examples, sends the x to a y, and the inverse function sends a y back to its x. Now I'd like to try a similar example, but this time we'll be using a graph instead of a table. So here we have in our graph the function g, and we'd like to find these various different things over here, g of 2, g inverse of 1, and g inverse of negative 1. So let's start with the first one, g of 2. Now we're working with the original function g, and 2 is the input, and we want to figure out what the output is. So 2 is really your x, and so we want to find x of 2 on the graph, and then we want to kind of go up to the graph and see what the output would be, and it looks like it would be a 1. So the answer there would be 1. Alright, now let's look at the second one. We want to do g inverse of 1. Now the key thing here is to notice you're dealing with g inverse, not g. So this 1, it's an input for g inverse, but that would make it an output on the original function g. So you're really looking for an output of 1, or a y value of 1 on the original function. And so that would be right here on the graph. And so we go over to the curve and back down, and you see that the answer there would be 2. And that makes sense because if g of 2 equals 1, then g inverse of 1 should equal 2, according to the property we learned before. In other words, the original function sends 2 to 1, so the inverse function sends 1 to 2. They do the reverse of one another. Now how about g inverse of negative 1? Again, we're dealing with a function g inverse, so that means this number in parentheses, negative 1, it's an input for g inverse, but it makes that an output for the original function g. So that means the y value would be negative 1 on the graph, which would be right here. And then we just have to go over to the curve and then go back up, and we see that the answer would be negative 2. Now once again, the original function g would send the number negative 2 to negative 1. So the inverse function does the reverse. It sends negative 1 back to the negative 2. Now I'd like to try to graph the function g inverse. Now the graph we have here already is the original function g, and we want to graph the function g inverse. And there's a fairly easy way we can do that. Remember that if the point a comma b is on the original function, then the ordered pair b comma a will be on the inverse function. So, for example, let's make a little list of ordered pairs that are on the original function. So let's just look at the graph and see if we can find specific ordered pairs that we know are on that function g. I'm going to take this one right here. It looks like that point right there is on it. And that would be a -5 comma -2. So let me write that one down. -5, -2. And the next one that seems to hit right on the crosshairs is this one, which would be -2, -1. So I'll write that one down. And then we have this one, clearly, 0, 0. And then this point here, 2, 1. And then it looks like this one, which would be 5, 2. So these are some of the ordered pairs that are on the function g. Now remember, the ordered pairs on g inverse, the inputs and outputs will be reversed. So if we want to make a list of ordered pairs that are on g inverse, over here, this first ordered pair, you're just going to interchange the x and the y. So it's going to be -2, -5. Because the input becomes the output and the output becomes the input. This point here will get switched around and become -1, -2. And I'll do the same thing on all of these. 0, 0 stays 0, 0 when you switch them. This one becomes 1, 2, and this one becomes 2, 5. And I'm just going to plot these points on the graph. So -2, -5 would be right here. Then -1, -2 would be right here. And 0, 0. And then 1, 2. And then 2, 5. Okay, and I'll just connect these now with a curve. And that would be the graph of g inverse. So if we have the graph of the original function given to us, we can just go down and find several ordered pairs that are on that original graph, and then interchange the x's and the y's, and then we can plot those. And that's an easy way to get the graph of the inverse function. So I'll label that one g inverse. Now I've just added a green dotted line, and that's actually the line y equals x. So that's the line where the x and the y coordinates are the same number, like 1, 1, 2, 2, 3, 3, etc. And that goes right up at a 45-degree angle through the origin. And notice that the two graphs that we have there, the original function g and the inverse g inverse, are reflections across that line y equals x. And that'll always happen. Okay, so if you reflect one graph across that green line, you get the other graph. So inverse functions always have graphs that are reflections across the line y equals x. In fact, if we look at this a little bit more closely, we can see that, this original point right here, -5, -2, when we interchange the coordinates, got moved to that point, -2, -5. So that got reflected right across that line. So, if you kind of went straight across there at a 90-degree angle. And the same thing would happen here with this point. And the origin doesn't move because it's right on that line. And then this point, and then this point. So each one of those points just gets reflected straight across that line y equals x when you interchange the x and y. Now, when we take the inverse of a function, if we get another function, then the function's called invertible. And not all functions are invertible, because sometimes when you take the inverse of a function, you get something that's not a function anymore, meaning you end up with something that has the same input getting sent to two different outputs, which wouldn't be a function. Now, a function is invertible if it's something that's called one-to-one, which means that each output originates from exactly one input. So to illustrate this, let's look at this function f that I've given here. So the function f sends these inputs to these outputs. So 1 gets sent to 3, 2 gets sent to 5, 3 gets sent to 7, 4 gets sent to 9. And that's what the function f does. It sends those inputs to those outputs. Now this is one-to-one. You can see that because every different x gets sent to a different y, and that's really what one-to-one means. So this is one-to-one. Let's write that down. So this is one-to-one. Now let's look at what f inverse would do here. I'm going to make a chart for f inverse, and again we'll put the input and the output. Now remember, the outputs of f become the inputs for f inverse. So the inputs will be 3, 5, 7, and 9. And f inverse would send 3 to 1, because it just does the reverse of what f does. F sends 1 to 3, so f inverse is going to send 3 to 1. And similarly, f inverse is going to send 5 to 2, and 7 to 3, and 9 to 4. And notice that this f inverse is a function. So it is a function. How do I know it's a function? Because each input gets sent to exactly one output. Okay? So in a function, you can't have the same input getting sent to two or more different outputs. And that's true here. Each input gets sent to exactly one and only one output. So it is a function. Okay, now let's look at this function. This is still a function because each input does get sent to exactly one output. The input 1 gets sent to the output 3, and that's exactly 1. The input 2 gets sent to exactly one output. It happens to be the same output as the other input, but that's okay. And 3 gets sent to exactly one output, and 4 gets sent to exactly one output. So it is a function, but it's not a one-to-one function, because you can see these two different inputs get sent to the same output. And one-to-one means every one gets sent to a different one over here on the right side. So this is not one-to-one. And I just wanted to show you what happens when we take the inverse of something that's not one-to-one. So let's take the inverse over here, and so we're still going to have our inputs and our outputs. And the inputs of the inverse are the outputs of the original, so they'll be the 3, the 5, and the 6. And 3 is going to get sent back to 1. And 3 is also going to get sent back to 2. And 5 is going to be sent to 3, and 6 to 4. But it's this part here that makes this not a function, because you see the same input is getting sent to two different outputs, and therefore this is not a function because of that behavior right there. So that kind of illustrates, if you start out with something that's not one-to-one, and then you take the inverse, you end up with something that's not a function. But as long as you start with something that is one-to-one, and you take the inverse, you'll always get another function, and that's what we mean when we say invertible. It means we start with a function, and we take its inverse, and it's still a function. even after we take the inverse. And that means the original function must have been 1-to-1 in order for that to happen. Next, I'd like to show you how you can find the equation of the inverse of a model. So in this example, we have a model, f of t equals 0.77t minus 43.18, that models the percentage of births outside marriage t years since 1900. And we want to find an equation for f inverse. So the first thing we want to do is we want to take our function and we want to try to think, what does this f of t stand for? And in this case, it stands for the percentage of births that are outside marriage. So I'm going to replace that with just a single letter. I could use a y generically, but I think this time, since it stands for a percentage, I'll use the symbol p. And we'll change that to a p when I write this equation down. You always want to do that. If you have a functional notation, you want to just put in some single letter for the dependent variable. And this expresses the percentage as a function of time. So what I mean by that is, if you know what the time is, you can plug that in and you can calculate what the percentage is. So that expresses the percentage in terms of, or as a function of, time. And to find the inverse, we want to interchange the inputs and the outputs. So we want, right now the t is the input and p is the output, but we want to switch those. So we'd like the t to be the output. We want that to be the letter that's on the left side of the equation, and p to be the input. So really all we need to do is solve this equation for t. So in order to do that, we would first add 43.18 to both sides of the equation. So that would give us p plus 43.18 equals 0.77t. And then we divide everything by 0.77 because we're trying to get the t to be alone. And when I write that down, I'm going to switch the sides of the equation and write the t first. So we end up with t equaling, and then we'd have 1 divided by 0.77, because this is really a 1p here. And if you do that on your calculator, 1 divided by 0.77 comes out to be 1.299 p. And then we have 43.18 divided by 0.77, which comes out to be plus 56.08. Now in this form, notice this expresses time as a function of the percentage, meaning if you know what the percentage is, you could plug it in and calculate what the time would be. Now the last step would just be to label this left side as the inverse function. So since the original function was f, and we've just found the inverse, we'll use f inverse, and the variable on the right side of the equation is p, so we'll have to do f inverse of p, because it's a function of p, equals 1.299 p plus 56.08. And that would be your inverse function. And again, what that would allow you to do is, if you knew what the percentage was, you could calculate the time. This left side really represents the time that it would take for the percentage to reach that amount. Now we also want to be able to find the inverse of a function that's not a model. So sometimes we're just dealing with an arbitrary function and not any particular application. And we'll do pretty much the same thing. Again, the first step would be to replace this functional notation with a single letter representing the dependent variable. And in this case, it makes sense just to use y, because since there's no application, there's no need to use any other letter to stand for anything. And y is the generic letter that stands for a dependent variable. So we'll replace that with y. And then we want to solve for x. We want to get x alone, because remember, an inverse function, you're interchanging the inputs and the outputs. Right now, x is being thought of as being the input, and y is the output. But we want to switch that. We want x to be the output, so we want that to be on the left side of the equation, because the output goes on the left side of the equation. And we want y to be the input, so we want that to end up on the right side of the equation. So we want x to be by itself. So we'll subtract 4 from both sides first. So we get y minus 4 equals 8/5 x. And then to get the x alone, we'd have to multiply by the reciprocal of 8/5. So we'd have to multiply both sides by 5/8. So I'll do that. So 5/8. Now 8/5 times 5/8 equals 1. So we just get 1x on the right side of the equation. And on the left side we get 5/8 y minus, and then we get 20 over 8, which reduces down to 5/2. Now let me just rewrite this so that the x is on the left side of the equation. So we've got x equals 5/8 y minus 5/2. And then we'll replace this x with the notation f inverse. So let me continue on up here. So remember, we started with the function f and we found the inverse, so we'll use f inverse notation. And the variable that goes in the parentheses is always the variable that's on the right side of the equation, so it would be the y in this case. So we'd have f inverse of y equals 5/8 y minus 5/2. And so far, that's pretty much the same exact process we used when finding the inverse of a model. The only difference here is when you're not working with a model, this variable that you're ending up with in the very end, you'll change to an x. So we usually would like this variable, instead of being a y, to be an x. So we'll change both these variables to an x. So we'll get f inverse of x equals 5/8 x minus 5/2. And that would be our answer. Now, when we're working with a model, we don't usually do that last step, because usually that letter stands for something, and so we don't just want to change it to something else because it has a significance. T stands for time, P stands for a percentage, etc. So we don't just want to change the letters at the end like that. But if we're not working with a model, usually we'd like the independent variable, or the variable inside the parentheses right here and on the other side of the equation, to be x.